This question deals with stoichiometry, and we're asked to basically do a calculation to determine how much air is required to burn off a given amount of octane. So, as all stoichiometric questions that we approach, we start with a balanced reaction. So, we're burning octane. You're going to utilize oxygen, and the products of a hydrocarbon being burned are going to be carbon dioxide and water. So when we balance the reaction, we get 2 moles of octane, 25 moles of oxygen reacting with it to produce 16 moles of carbon dioxide and 18 moles of water. Now, in addition to that, we're told that we have a liter of this octane, and we're told that the density is zero point 0.7 grams per milliliter. So first we convert that 1.0 liter to milliliters so that we have consistent units with the density that we're given. And when we perform that calculation then based on milliliter volume, we get 700 grams then of octane. Well, let's convert that then to moles, the molar mass being 114 grams per mole of octane. And ultimately, here's what we need to know. For stoichiometry, we want to always find out how many moles of a substance are involved. We're going to burn then 6.1 moles of octane. So let's then relate that to the oxygen that's involved based on the balanced reaction. So according to the balanced reaction, for every 2 moles of octane that we burn, 25 moles of oxygen are required. So let's go ahead and do that step in the process and see where we're at in terms of moles of oxygen. So ultimately, when we complete the calculation, um, we determine that 77 moles of oxygen then are going to be required to burn off this amount of octane. Now we need to put that in terms of volume because that's what the question asks for. So the ideal gas law is what we're going to apply. PV equals nRT. Told the pressure is 1 atmosphere. Of course, we have 77 moles of oxygen. The gas constant is 0.082 liter atmosphere per mole Kelvin. And the temperature they gave us was 20 degrees C. But we must remember that we always have to have Kelvin for the temperature that we use anytime we use any of the gas laws. So we converted that to Kelvin at 293 Kelvin. And so when we solve for the volume of oxygen required, and we're going to keep a little extra significant figure for now here, we get 1,850 liters of oxygen that are required to burn off that octane. Now they ask us what volume of air is required. So there's an additional step we need to take here. So the final step in the process then is to recognize from what they told us, 22% of the air consists of the oxygen. So the final calculation we have is this is the volume of oxygen required. However, we want to find this volume of air, 22% of which consists of this volume of oxygen. So we need to do a division here to find out this factor right here, the volume of air required. And when we perform that calculation, we end up getting 8,400 liters of air being required to ultimately burn off the octane in this problem.